Good day, erudites. This is Next Level Catch-Ups 2.0, General Physics 1 edition. This is Daniel Pasqua, your lecturer, and today we will be continuing in our previous discussion regarding Lesson 5, Projectile Motion, wherein in this video, I will be providing you some examples for the different cases of projectile motion. Now, projectile motion is a fundamental concept in physics that describes the curved path an object follows when launched into the air, influenced only by gravity and the initial velocity. Understanding this motion is crucial for accurately predicting trajectories in fields like mathematics, engineering, and science. For example, athletes use it to optimize throws and jumps, engineers apply it in designing bridges and roller coasters, and military systems rely on it to guide missiles and artillery. Mastery of projectile motion enables us to precisely control and innovate across diverse real-world scenarios. Now, before we head over to our examples and sample problems, let us do a recap on what we've discussed. In physics, or in projectile motion particularly, we have the following assumptions. The effect due to air resistance is negligible. The effect due to curvature of the Earth is also negligible. The effect due to rotation of Earth is negligible. And the acceleration due to gravity is constant within the span of the trajectory and the projectile taken by an object. Moving on, we have different cases in projectile motion. In case number 1, the object of projection is on the ground level where it is projected at a certain angle theta. Case number 2, we have the angle initially elevated at a certain height h, horizontally projected, and it has the angle of projection which is equal to 0 degrees. Then finally, we have the case number 3, wherein the projectile is initially elevated at a certain height of h, and it is projected at a certain angle of theta, where it is not equal to 0 degrees. We also have the different equations in projectile motion, where it is divided into 2, vertical and horizontal equation. For vertical equations, we have 3. The first being the final velocity is equal to initial velocity multiplied by the sine theta plus gravitational acceleration multiplied by time. Second being the vertical displacement is equal to the quantity initial velocity multiplied by sine theta multiplied by time plus gravity times t squared all over 2. And then we have the final velocity squared is equal to the initial velocity sine theta squared plus 2 gravity multiplied by the vertical displacement. And then for horizontal equation, we have 1, which is the horizontal displacement is equal to the quantity of initial velocity multiplied by cosine theta multiplied by time. Moving on, we will be solving and answering some sample problems. Sample problem number 1. At the Araneta Stadium, an athlete threw a javelin at an angle of 60 degrees with a velocity of 65 meters as shown. Calculate A, the vertical and horizontal component of the initial velocity, B, the maximum height achieved by the trajectory of the javelin, and C, the total time taken by the projectile. Assume that the projectile leaves the foot at the ground level, ignoring air resistance and the aerodynamic structure of the javelin. For sample problem number 1, we are given the initial velocity of 65 meters per second and the angle of projection, which is 60 degrees. Now, to solve for letter A, we have to solve for the horizontal and the vertical components of the initial velocity. So, the formula to solve for the horizontal component is initial velocity multiplied by cosine theta. So, to solve, we have to substitute our values, which is 65 meters per second multiplied by cosine 60 degrees. Then if we input it in our calculator, we get the value 32.5 meters per second as our horizontal component. Moving on to solve for our vertical component, we have to use the formula initial velocity multiplied by sine theta. So we substitute again, 65 meters per second multiplied by sine 60 degrees, and then we input in the calculator, we get the answer 56.29 meters per second as our initial vertical component. Moving on, let's solve for letter B. Now, for solving the maximum height or the vertical displacement, we can use, in this case, the third formula, which is the final vertical velocity squared is equal to the initial velocity multiplied by sine theta squared plus 2g dy. This is because for solving for maximum height, we can assume that the vertical final velocity is equal to 0, as when the ball reaches the height, its vertical component is or at its lowest, or it is at 0, as from there the projectile starts to go negatively or downwards. So with that in mind, let's try to solve it. So we can assume this is just 0 squared and is equal to our vertical component, which is 56.29 meters per second squared plus 2 multiplied by our gravitational acceleration, which is negative 9.8 meters per second squared, and then our d's of y. Now, solving for maximum height, of course, we have to isolate our d's of y. So we can just put it in one side, then we can transpose and multiply, divide both sides, so we can get the answer. So that is just transpose 56.29 meters per second squared all over 2 multiplied by our gravitational acceleration. So we can cancel our units, meters cancel, rather the seconds cancel, meters here cancels, this cancels, and we're left with meters. So this would equate to our d's of y will be equal to 2.87 meters. Lastly, we are to solve for letter C, which is the time total. So we can use the first formula, which is final velocity is equal to initial velocity sine theta plus gt. So we can try to solve this for the times going up, so that our final velocity will equal to 0. So let's try it. Let's input our values. Let's say that our final velocity is equal to 0 as the trajectory goes up. Then we substitute 56.29 meters per second plus our gravitational acceleration, 9.8 meters per second squared, multiplied by times going up. Then we isolate times going up. Let's put it in this side. Then we either transpose or divide both sides. So we have negative 56.29 meters per second all over negative 9.8 meters per second. Then we cancel our units, meters cancel, seconds cancel here, square root of the seconds cancel here, and then we are left with the time going up is equal to 5.74 seconds. And now we are not done yet, as this is only the time going up. Since our example is the case number 1, which is going up and then down of our projectile, we can say that the time going up is also equal to time going down, since our projectile is horizontally elevated, or there is no elevation as it is on ground level. So we can see that times going up is just equivalent to times going down. Therefore, we can also say that our times, or the total time, is just equal to time of up times 2. So let's try solve that. Our time total is equal to 2 multiplied by 5.74 seconds, which just leaves us with the answer of 11.48 seconds. And that's how you solve for sample problem 1. Sample problem number 2. Evaluate the motion of a soccer ball projectile, initially elevated from a skyscraper that measures 800 meters above the ground and to be kicked horizontally with a velocity of 20 meters per second. Calculate A, the vertical and horizontal component of the initial velocity, B, the total time taken by the projectile, and C, the maximum horizontal displacement of the soccer ball, ignoring air resistance and the rotation of the ball. For sample problem number 2, we are given the height of 800 meters and the initial velocity of 200 meters per second. So for letter A, we are trying to solve for the vertical and the horizontal component of our initial velocity. Now notice in our problem that we are not given the angle of projection or angle theta, but we can infer, as it is in the case number 2, that when a object is projected, elevated at a certain height, and then is horizontally or is moving at a horizontal projected at a horizontal velocity, we can infer that the angle theta is equal to 0 degrees. So with that in mind, we can solve for the horizontal and vertical component. So let's just substitute our values. This is just 20 meters per second multiplied the cosine of 0 degrees. That will just equal to 20 meters per second. And then for our vertical velocity, that is 20 meters per second multiplied by sine of 0 degrees, which is just 0 meters per second. And that is our vertical and horizontal component of our initial velocity. Moving on, we are trying to solve for the times going downward for letter B. Now we can use the second formula in our vertical projectile motion or equations, which is the vertical displacement is equal to the quantity of initial velocity multiplied by sine theta multiplied by times going down plus gravity multiplied by times going down squared all over 2. So we can just try to input our values. So our vertical displacement is just 800 meters, but take note when we're solving for in case 2, we should always take in mind that our vertical displacement is negative as the projectile is going down. So this is also to ensure that when we're trying to cancel the units, we are going to have the correct and most accurate value and also the units. Okay, so moving on. So the vertical component is just 0 meters per second multiplied by times going down, and you know that any number or value multiplied by 0 is just 0. So this, you can just disregard or cancel that. Plus our negative or our gravitational acceleration, which is negative 9.8 meters per second squared, multiplied by the times going down squared all over 2. Now, since we're trying to solve for times going down, we have to isolate times going down. So to do this, let us just transpose and also to divide both sides. So let's just isolate and put our time here. And then we have negative 800 meters divided by, so negative 9.8 meters per second squared divided by 2 is just negative 4.9 meters per second squared. Now, to solve thoroughly, we can to cancel the squared here. As you can see, for the times, we have to square root both sides. So then we go ahead and cancel the units. Meters cancel, and since the we are using square root, we cancel this here, this cancels, and also the square root cancels here. So we are left with our times going down is just equal to 12.78 seconds, and that's for solving letter B. Then lastly, we have to solve for letter C, which is solving for the range or the horizontal displacement. So this is very simple, as we are given our horizontal component and our time. We can use the the first and only ever equation in horizontal projection, which is the d of x equal to quantity initial velocity multiplied by cosine theta multiplied by time. We can also just use this as times going down. Therefore, so let's just substitute our values. D of x is equal to 20 meters per second multiplied by times going down, which is 12.78 seconds. Then we solve, we are left with 255.6 meters. And that is our final answer. Lastly, sample problem number 3. Sample problem number 3. Evaluate the motion of a projectile initially elevated at 20 meters above the ground to be launched at an angle of 45 degrees and with a velocity of 14 meters per second. Calculate A, the vertical and horizontal components of the initial velocity, B, the total height achieved before reaching the ground, C, the total time of trajectory, D, the total horizontal displacement, and E, the final velocity vector, and F, the angle made as it hits the ground. For sample problem number 3, we are given the height of 20 meters, angle of projection which is 45 degrees, and the initial velocity of 40 meters per second. So for letter A, we are trying to solve for the vertical and horizontal components of the initial velocity. So as we've done before, we should just substitute our values. This is 40 meters per second multiplied by cosine 45 degrees, which comes about to 28.28 meters per second. And then for the vertical component, that is just 40 meters per second multiplied by sine 45 degrees, which just comes about to 28.28 meters per second. That's for our vertical and horizontal components of the initial velocity. For letter B, we are trying to solve for the maximum height or the height total. So to solve this, we need two parts. Since we have the case number 3, which is we have the angle projected at a certain height or elevated at a certain height, and then the angle is not equal to 0. So So that means that we have two heights: the height of the elevation and also this vertical displacement of the projectile before it reaches the same height of where the object is first elevated. So we have the first step, solve for d of y, and then and then the second step, we just add the height and the vertical displacement. So let's go for number 1. We can use the third formula of our vertical projection, which is final velocity multiplied by VO sine theta squared plus 2g dy. So again, since for solving dy, we are trying to solve for the angle of projection going up. So we can say that when it reaches its peak height, or the d of y, our initial final velocity is just 0. So we just keeping that in mind, we substitute our value. 0 squared is equal to 28.28 meters per second squared plus 2 multiplied by negative 9.8 meters per second, which is our gravitational acceleration, and then multiplied by d of y. So we isolate d of y to the other side, d of y, then we just transpose and divide both sides. We're left with 28.28 meters per second squared all over negative 19.6 meters per second squared. We cancel our units. The seconds cancel here, second cancels here, meters cancel here, and then we're left with meter, and that's just gives us the vertical displacement of 1.44 meters. Then we go to step number 2, where we add both the height and the vertical displacement. So that is 20 meters for the height plus our answer, which is 1.44 meters. So therefore our total or maximum height is just 21.44 meters. That is letter B. For letter C, we are trying to solve for the total time of the trajectory. So we have 2 steps: solve for the times going up and times going down. This is because since it's elevated at a certain height, we have the time going up. That is because of we are given an angle not equal to 0, and then from that initial point, from its peak height, we're going down. So t of the times going down. So let's solve for the first step. We can use the first formula for the vertical projection of projectile motion, which is v of final velocity is equal to initial velocity multiplied by sine theta plus gravity times t is going up. Since we are our projectile going up to its peak height, we can see again that our final velocity is equal to 0. Then we substitute our other values. Our vertical component is just 28.28 meters per second plus the gravitational acceleration multiplied by times going up. Then we isolate times going up. We just go ahead and put it in this side, and then we transpose and divide both sides. We are left with 28.28 meters per second all over negative 9.8 meters per second squared. Then we check our units. We cancel the meters cancel, seconds cancel, square cancels here, so we're left with the seconds, which is correct. And then we are left with times of up is equal to 2.89 seconds. Then we move on to step number 2, solving for the times going down. Now take this very note that for solving for times going down in case number 3, we have to use the total displacement for the d of y. This is because we are calculating for the times going down from the very peak of its height, or from the very peak where the object starts to go down. And then we have also to take note that the theta should be equal to 0. This is because, as I said earlier, that we are starting from the very peak, so therefore the theta should always be equal to 0 degrees, or rather the projectile is starting from the positive horizontal axis, which is just 0 degrees. So we substitute, this should be negative since we're going down. This is negative 21.44 meters, and any value multiplied by sine 0 degrees is just 0. So this is just 0 meters per second multiplied by t at time going down. And remember, anything multiplied by 0 is just 0. This thing cancels. So we have plus the gravitational acceleration multiplied by t of down squared all over 2. Then we just isolate t of d. So we have t of d squared is equal to negative 21.44 meters all over. So negative 9.8 meters per second squared divided by 2, that is negative 4.9 meters per second squared. Then we cancel our units. This thing cancels. And then we see here that the times down is raised to 2, so we have to solve for the time, we have to square root both sides. So this squared cancels, this cancels, and then you see these seconds is also squared, so we cancel that. So when you put that into our calculator, we have the t's going down will be equal to 2.09 seconds. Oops, 2.09 seconds. And then for solving for the total time, you have to add both of these values, which is the t's of up and also the t's going down. So we just substitute, that is 2.89 seconds plus 2.09 seconds. Now we add this up and then we are left with 4.98 seconds, and that is for letter C. For letter D, we are trying to solve for the range or the horizontal displacement. This is very easy as we are going to use the horizontal displacement formula. So we just substitute our values. This is 28.28 meters for the horizontal component multiplied by our total time, which is answered before, 4.98 seconds. The seconds cancels. Then we are left with meters, and then when you put it in our calculator, this is just equivalent to 140.83 meters. That is for letter D. For letter E, we are trying to solve for the final velocity. So we have 3 steps solving for the horizontal and the vertical components of our final velocity, and then we are using the Pythagorean theorem to solve for the final velocity. Now for step number 1, solve for the horizontal component. Now take note that in projectile motion, the horizontal component is constant regardless of the elevation or the angle of projection, whether it is high, low, or there is no angle, it is horizontally projected. The vertical or the horizontal component is always constant. So that means that our initial velocities of x is just also equal to our final velocities of x. So therefore, we can say that our final the horizontal component of our final velocity is just equal to 28.28 meters per second. Moving on. So step number 2, solve for the vertical component. So we use the first formula in our vertical projection equation. So we can simply substitute our value. So this is our vertical component, 28.28 meters per second, plus the gravitational acceleration, and then multiplied by our total time, which is 4.98 seconds. So we put this all in our calculator. This is just equivalent to negative 20.52 meters per second. Now, for step number 3, we have to use the Pythagorean theorem to solve for the final velocity. So let's do b of f squared is equal to 28.28 meters per second squared plus our vertical component of the final velocity, which is negative 20.52 meters per second and squared. Notice that our final velocity has the exponent of 2, so we have to get rid of that. So we square root both sides. So this cancels, and then we are left with solving what's inside this radical. So we can say, if you put it in our calculator, this is just equivalent to 34.94 meters per second. Then, since we are trying to solve for the vertical component or the final, we are trying to solve for the final velocity. It is important to direct where is it going from. Now, since we can observe from our graph, our illustration, as it goes down, we can notice that it is around here. So therefore, we can also say that the final velocity is directed towards quadrant number 4. And that is our letter E. Finally, we're solving for the theta final or the final angle of projection. So we can use the inverse tangent of our vertical component over the horizontal component of our final velocity. So we just substitute our values. The inverse tangent of negative 20.52 meters per second all over 28.28 meters per second. Then this just cancels. Then in our calculator, that is just equal to negative 35.96 degrees. Now, since this is a negative side, we can just put this in our counterclockwise by adding 360 degrees. So 360 degrees minus, or rather plus, negative 335.96 degrees. This is just equal to 324.04 degrees from the positive x-axis. And that is our final answer. We are done with our sample problems. And now for some takeaways. Practice makes perfect. In solving for projectile motion in physics, it is very difficult at first as we are not very familiar with this kind of concept. So it is very important to analyze different problems by doing other sample problems that we can use or we can find in the internet or other sources that can provide us with different cases of projectile motion, being it case 1, 2, or 3, and with different given, may it be the height, the initial velocity, or the angle theta. That is all for this lesson. Thank you, erudites, for listening, and I hope you learn a thing or two about projectile motion.